It's a great pleasure to have Chris Booth from Gatan here with us. He's going to, in fact, Gatan is one of the sponsors. We would like to thank them for sponsoring us, and they came forward for sponsoring this event. We should thank them for that. And applications of electron counting detectors, detection cameras in high resolution cryo-EM. So he's going to talk to us about the exciting developments in the direct detectors and related topics. Thanks. Chris will introduce himself.
Great.
Thanks.
It's my first trip to India, and it's really terrific. I appreciate the organizers giving me a chance to come here, and it's a beautiful site. I can't be happier. So, my name is Christopher Booth. I work for Gatan Incorporated. I originally did my PhD in cryo-EM, so I actually was a student of WatchU before I got into sort of the business side of this, working for Gatan. Since I've been at Gatan, I've done a number of. I used to be as a software engineer, so I was developing some software programs at Gatan. And then from that, it sort of evolved into some different 3D imaging techniques. And now I'm a product manager at Gatan, so my responsibilities are for all of the life sciences at Gatan. So if you're interested about this, I'm happy to talk to you. If you have other questions about other life science projects that maybe we could help with, I'm certainly happy to answer those questions as well. All right, so this course is extremely comprehensive, so I really hope that I can add something to what you've already heard today. Today I'm going to really focus on what our cameras are doing in this, for this particular field. So I'll start with this slide. Some of you may have seen this slide before. Really to explain some of the differences between cameras that we've been doing in electron microscopy for a very long time and sort of the new generation of direct detection cameras. So on the left here we see what is typically, it's a scintillator-based camera. So what happens in these types of cameras is that you have a layer of material on the surface, and an electron beam comes down, strikes that material, and creates a photon of light. That light then propagates through the material until it strikes another chip, a CCD or a CMOS chip, where it's then read out. And this is typically found in the Orias cameras that we make, the ultrascan cameras that you may be familiar with, and this new camera that we have called the OneView camera. Okay, and this is sort of the successor to the previous generations of scintillator-based cameras that we have. On the other side, we have these direct detection cameras. Now, these cameras don't have an intermediate way of detecting the electrons. The electron actually strikes the sensor. It strikes the sensor directly, and in most cases today, most modern devices, the electrons will actually pass through the direct detection device and fall into a space below the sensor. And so the real advantages of this type of device are that it gives you a much more localized signal in response to the electron event. And what we're showing on the bottom here are Monte Carlo simulations of electrons passing through a detection device. So on the left, we see an electron strikes here, and we've simulated something like 1,000 tracks. And you can see that the electron then decays through the material in this cloud shape. And what happens is everywhere that this electron passes through this top material here, it actually generates light, and that's what we detect on the camera. Whereas with a direct detection device, you can see that the electrons pass through the device, and there's actually a very narrow region which actually does the detection of the electrons. And this gives us a much sharper, more precise estimate of where the electrons struck the sensor. And so this gives us improvements in resolution, things like that. And that's true for all direct detection devices. So before I get into too much more detail there, I'm going to start giving you a little background on our OneView camera. So the OneView camera is our successor to the ultrascan camera. This previously was our highest end camera for electron microscopy. These are scintillator-based cameras, and what we've really focused on with this camera is that we're making all of our cameras go a lot faster. And so that has some consequences which are beneficial, which I'll try and talk to you about today. So the speed of these cameras, typically, speed of this camera is 25 frames per second, and so that's 25 full frames per second. And so that has some interesting consequences that we can use that information that's coming in relatively quickly to do some nice things with the images. So to start with, It's good for traditional imaging. If you're in a general purpose lab and you're looking at lots of different kinds of samples, this is a great detector for people who are new to electron microscopy, people who are doing general purpose work. In the life sciences, we see lots of nice looking traditional image samples are prepared and they look really good on this kind of camera. This is a collagen fibril. Similarly, if we're looking at skin cells, you can see nice preservation. You can see the details of sort of traditionally stained samples as well. The thing I want to talk about primarily with this camera is how we take advantage of this speed. And so what's really interesting about this camera is we've integrated live drift correction into this particular camera. So when you're collecting images with a camera, if there's any motion of the sample, and that can actually happen with plastic sections, there'll be slight motion, you can start to try and correct for this motion so your images look sharp. And I'm going to give you an example of this in the next case here. So there are many things that can cause motion or drift in the samples. Environmental, thermal, beam-induced motion, even the stage might be drifting. And these are things that we have some ability to correct for. And even subtle drift can cause a blurring of the sample through the exposure time. And so what I'm going to show you is one example where this is actually a graphite sample, so it's not a biological material, but the idea is that we just started exposing the sample to the beam, and you can see what happens. And this is actually relatively common in many types of samples, that the beam jumps or starts to move around a little bit while the beam hits the sample. And so what's really nice is that if you have a camera that's working quite quickly, you can take those frames and you can start to align them together to correct for this kind of drift. And so if we took that movie and we summed all those frames together, we can see that the image is blurred out in this direction, right? But what happens in the software, because this camera is moving fast enough, is that it is constantly trying to align the frames to each other. And so instead of seeing an image like this that's output, you can actually see a nice crisp image that looks like this. And so for general purpose microscopy, this is a really nice way of making use of the relatively high speed of this camera at the full frame rate. Now, the real reason that I put this camera in this slide presentation, so this is a nice thing to do, but Lou was kind enough to introduce microelectron diffraction to the audience. So what's happening is, and Tamir Gonen has pioneered a lot of this work, is that people are starting to take X-ray crystallography samples that are too small to use in X-ray crystallography. So there's these nanocrystals, and try and do tilt series and collect the diffraction patterns. And this camera is really good at collecting diffraction patterns. And one of the things that's nice about it, now this isn't a micro-ED sample. This is a proof in principle of sort of a semiconductor crystal sample, but we're excited about the prospects for this camera in that kind of space. And so what you're seeing on the left here is that much like you might expect in a, much like you might expect in an actual crystallography experiment, we see a relatively quick, continuous turning of the goniometer and collecting a diffraction pattern while we're tilting that sample. And this is the kind of camera that actually does really well for those types of experiments. So if you find yourself in a situation where people have these types of samples and you're looking at collecting diffraction patterns, this may be a camera that's interesting for you to take a look at, in addition to all the other general purpose imaging uses that you might have for the camera. Okay. So that's all I'm really going to say about the scintillator-based cameras, and today I'm really going to focus my talk on the direct detectors, which we're very excited about and has caused quite a big shift in what's going on in cryo-electron microscopy. So we have two types of detectors which are used, which are direct detectors. We have the K2 Summit, which is an electron-counting direct detection camera, and we'll talk about what that means a little bit. And we have an energy-filtered version of the K2 Summit. And so for those of you who aren't aware, an energy filter is kind of like a prism. It allows us to select for only a certain wavelength of electrons to strike the camera. And I'll show some examples of this a little bit later. But this is a way of helping to improve the signal noise and the contrast of the electrons that actually strike the detector itself. And it's very common in tomography, as we'll see in a second. So these two cameras, they both operate at 400 full frames per second. And again, I'm going to talk about why the speed is important. They have a direct detection sensor, which we've talked about a little bit. The performance of these is really at the forefront of what these cameras can do. And the K2 Summit is really great for high contrast on single particle work, relatively thin specimens. And for high contrast with thicker specimens, that's when you really want to be using an energy filter type camera. Okay. So the progress in this field has been really tremendous. The recent paper set the benchmark for the highest resolution structure to date from single particle work, and that's this 1.8 angstrom structure from the Sriram's lab at the NIH, again, using one of our detectors to solve this structure. And what I wanted to highlight here is from a review article that came out this spring. And they talk about, and we'll talk about what DQE means in a second, but DQE is the way that we tend to characterize our cameras and characterize the performance. It's really a signal-to-noise measurement of our cameras. And the highest values can really only be obtained in a counting mode. And their comment in this article was at present, only the K2, when operated in counting mode, can produce a DQE as high as this with reasonably small exposure times. And that's something that I'm going to try and expand on and explain as we give this talk today. Okay. So, last year, about this time, we started making curves that look something like this. So what this curve is we have the size of the molecules on the left here, and we have the resolution of the structure on the right. And the goal of this structure, this curve that we were making, was to try and understand what our entitlement was. What should we be able to achieve with this camera? And we were going about this by just looking at the publicly available data and starting to try and plot all of the existing structures that existed. So this is what the world looked like a year ago, and it's hard to express how fast this field is moving. In a year, this curve has now shifted farther to the left and farther down. And so I'm going to make a couple of very important points, I think, on this particular curve. So there are these new structures. So there's this 1.8 angstrom structure that pushes the curve, this curve out to the left here. And then there are a couple other structures here, and I'll touch on this for a second. The takeaway from these types of plots is not that everyone should expect to get 1.8 angstrom resolution, but we use these plots to try and tell us what can we achieve if the camera is limiting you, okay? So many structures, many real biological materials are going to be heterogeneous. They're going to have lots of challenges in high-performance imaging. But what's really exciting about what we're seeing in this curve is that we are seeing smaller molecules being able to be studied. And it's actually some of these structures in here, which aren't at the very tip of the resolution, but these are the real interesting science, is these dynamic structures, these heterogeneous structures. And what we're seeing is that the structures coming from these K2 cameras is really shifted down toward the lower left-hand side of this plot. So we're able to see smaller molecules, and we're able to see higher resolution structures for a particular system, which is really what's exciting for us. Okay, so I talked about counting, and what is counting? Well, when we're imaging at 400 frames per second, we're not actually collecting images that you can really interpret. What we collect are images that look like this. Somewhere in there is information from your sample, but it's really hard to see. What we're actually doing is we're seeing electron events, we're seeing where the electron struck the sample. And only when you take many of these images and start to aggregate them does the information about your sample start to become present. So what I want to show you in this particular image is that the raw data, electrons striking the device, looks something like this on the left. It's kind of messy, and there's big peaks and little peaks. The size of the electron peak really doesn't have anything to do with your sample. The size of the electron peak really relates to how the electron passed through the device. If it passed through, happened to strike an atom and sort of decayed in a funny manner, you'll get a very big peak. Whereas if it just passes straight through, you'll get a smaller peak. None of that relates to your sample. And so what we're doing with electron counting is we're only detecting the place where the electron struck the device. We're not measuring all this noise related to how it's being detected. Okay, and so on the left is the raw data, and on the right is what an electron-counted frame looks like. Okay, and actually I took these slides out, but this is the place where I usually have the rain slide. And so the analogy here, well, actually, I'll do that in 1 second here. So let me talk about how this counting works for a second. So you'll hear about many cameras, and a lot of discussion about this integration mode. And so what does integration mode mean? Well, integration mode, and the K2 Summit also has an integration mode that can be used. The electron enters the device, it scatters in some direction, and there's some charge that builds up on the surface of the device. And what happens is that these pixels read out the local charge that's present, that's collected in each well of the pixel, okay? And so if you see the charge in each of these wells, and you collect that charge and you accumulate it, that will form the image that you're looking for, okay? What happens with counting mode is we take this information and we make an estimate of where the electron would have struck the device given this decay pattern of the electron. So we actually have some people with a particle physics background, and the analogy here is that they look at in particle physics, they look at particles striking their detectors, and they'll have these funny decay patterns, and that gives them some information about what particle it was and where it was. So in our case, we know that it's all electrons, but we look at the decay pattern and try and estimate where the original electron landed on the device. And so that's what we say right here. And now we go a step further, and it has some advantages. We don't just try and say which pixel the electron struck first, but we try to do a little better than that and say, we think the electron actually landed in the top right quadrant of this pixel. Okay, and so then we're trying to refine the positioning of where these electrons struck the device to better than a pixel resolution. Okay. All right. So I'm going to talk a little bit about I'm not going to go in much detail about DQE, but I just want to give you a quick pass through DQE. The way we think about DQE is we always think in Fourier space. So in this audience, maybe many of you are very comfortable thinking in Fourier space. For those of you who might not, if you think of a sound wave, and you look at the FFT of the sound wave, that's what you see as the bass and the treble in your equalizer of your stereo system, okay? So you have lots of bass components, low frequency components. You have lots of treble components, the high frequency components. Well, we do the same thing with images. We will have an image, we will do a Fourier transform of it, and we will see lots of low frequency components which are at the origin of the image, and we'll see lots of high frequency components which are at the edge of the image. Okay, and this is pretty normal. This is what people generally understand. So when we look at two different images, you can see we have a relatively crisp looking image and we have a relatively blurry image. And you can see if we look at the Fourier transform of these two images, we see one that has lots of high frequency components, and we see another which has relatively few low frequency components. And when we're looking at DQE curves, what we do is we'll take an image like this. Well, okay, so this is the way to think about DQE curves. This is not actually the way DQE is calculated, but we'll take a Fourier transform of an image, and if you look at its rotational average around from the origin to the edge of the image, you can see a plot that looks something like this. And if we think about the signal to noise at each frequency, that sort of roughly corresponds to the peaks of that plot. If you look at the signal-noise ratio at each frequency component, that's actually what DQE is. So if you see a DQE curve that's relatively high here and falls off at the end, that's a better DQE curve than if you see one that falls off quickly and sort of goes along zero for the rest of the image. Okay, so that's rather than getting into the details of calculating DQE, that's how I think about DQE when I'm looking at it. Now, I'm not going to say very much about DQE, but I did want to show this one curve highlighting the DQE of our cameras. So DQE is our signal-to-noise ratio as a function of spatial frequency, okay? And what I want to highlight here, so we have very strong signal-to-noise ratio for low-frequency components, and it falls off as we get to higher frequency components, okay? And really, the takeaway from this particular image that I want everyone to take away with is that our DQE curves for a 200 kV microscope and a 300 kV microscope are really very close, okay? And that's not the case for most detectors. So we've been able to engineer the K2 camera so that you can use it at 200 kV and still have excellent performance. And that's something that I think it's important to understand. Most of the DQE curves that you see people report only talk about the 300 kV curve and sort of ignore 200 kV. But most people have 200 kV microscopes, and so that's what I want you to remember when you take away from this. Okay? So in this is actually the place where I usually have the rainfall slides. And so we had a nice example of this during Lou's talk. The rain came down really hard. And the example is that you can think about electrons raining down on the sensor, and we need to be able to tell each electron apart. And the faster the rain comes down, the harder it is to tell apart those electron events. And so that's kind of the analogy here when we're thinking about detecting electrons. So if we have a fixed dose rate, so we have a fixed rate at which the electrons are raining onto the sensor, if we have a camera that's running very, very fast, so at 400 frames per second, we get a result that looks something like this. Whereas under the same conditions, if we have a sensor that's running at 40 frames per second, we have a result that looks something like this. And so what this says is for this dose rate, so this speed at which electrons are passing through the sample, it's really challenging to start to isolate the electron events from each other, and you really can't do it. And that's what makes counting really challenging when you're running with lower speed cameras. So with a higher speed camera, you start to have a chance to really separate these events and identify different electrons that are in the sample. Okay? So with this speed comes a couple of advantages. So the same story that I started to tell you, that I told you about the 400, oops. There we go. Okay. Okay. So it's a similar story to what I was telling you about the one-view cameras. When you have a fast camera, one of the first things you can do is collect frames and start to align those frames. So if we have a relatively long exposure here, you can see that it was sort of drifting during the exposure. And if we start to frame correct those images, it's running live here. If you correct for the drift in those images, you can align these frames so that the same feature is on top of the same feature in every subsequent image, right? And so that's the first advantage you get from speed. And if I just zoom into this particular region, this is graphite. And you can see, if you look closely at this image, so the bottom left is the graphite sample that has been aligned with drift correction, and the top right is without drift correction. Now, this is graphite, so we should expect to see graphene lattice sheets in this. And if you look really closely, you can see the information is there, but it's blurred out, it's less clear. And so frame alignment gives you the opportunity to actually see the graphene lattice that you're looking at. And with the K2 cameras, we've often called this dose fractionation. So we're taking a single exposure and we're splitting the dose among many different frames, right? Okay, and now there are many examples of this with real biological materials. This happens to be a ribosome sample, but in the original exposure of the image, you see a Fourier transform that looks like this. And to people who've done this, what you see is you see Fourier components in this direction, so good resolution this way, but in this way it's blurred out, right? So if we align those frames together, we can see nice round tone rings. We see information in this direction and in the other direction. So we're not losing that high frequency information this way. We're not blurring out our images. And this, to be honest, when we started the K2 project, we didn't know how important this was, but this is standard. This is something everybody has to do for doing high performance cryo-EM today. Okay, but the second thing I want to mention is, all right. The second thing I want to mention is just to walk you through how those images are collected so that when people are talking about doing counting with a slower camera, you can sort of try and think through the process of what has to happen so you can understand it better. So as we looked earlier, a raw counted frame might look something like this. Now I've zoomed in a little bit to make it clearer to see the particular parts of the image, but a raw counted frame might look something like this. And a final aligned image might look something like that, right? And so the steps in the middle are actually important when you're thinking about buying a camera. So let me walk through this for a second. All right. So when you're doing counting, this is what happens. When you're counting, you get one raw frame at 1/400th of a second. You get the next raw frame at 1/400th of a second, and you accumulate a number of these frames to get a subframe. Now, the signal and noise in the subframe is not terrific, but it has enough signal and noise that you can start to see the specimen in the image. And when you have enough information like this, then you can take this image and the next 1/10 of a second, and the next 1/10 of a second, and the next 1/10 of a second, and you can align these frames to each other and to try and correct for drift down to about 1/10 of a second, right? So any drift that happened between these frames, you can't correct for, because the raw counted frames, they don't look like your image. They look like this starry sky, and you won't be able to align this frame to this frame. There's not enough signal and noise in those frames. But you will be able to align this frame to this frame to try and correct for drift. And so the consequence of that is that, the consequence of that is that if you're trying to count with a camera that runs at 30 frames per second, your subframe exposure time, instead of being 1/10 of a second, might be a whole second. And so that means that any drift in your microscope that happened during that second, you won't be able to correct for. Okay, and it's kind of a hard concept, and to be honest, I've tried probably a half dozen different ways to explain this, so if it's not clear, please do come and find me, and I'll try and explain that a little better. All right? Okay. All right. Right, so now we looked at this curve a little bit earlier, and one of the features that I didn't highlight to you was the difference between the circles and the triangles. And what we're starting to see is that we have a number of structures that are really at the limit of resolution, or what we think we can achieve, that are coming from the energy filtered version of the camera. Okay? And especially a number of very small structures that are coming from the energy filtered version of the camera. And I want to take a second to talk a little bit about why that might be as we go through this year. So when Sriram published this 2.2 angstrom structure of beta-galactosidase, one of the quotes that was in that article was that he made the comment that improved image contrast and maximization of amplitudes at low resolution allowed us to go closer to focus and still correctly pick particles. Now, you may remember there was a big controversy about going close to focus and picking particles, and there was one particular group which published a structure which had been challenged, and one of the arguments is that because they went close to focus, they weren't sure if they were picking particles or not. And so it's really important that if you're going close to focus, you're able to see the particles well enough to pick them and align them. So the K2 camera, we've really got quite high signal noise ratio at these low spatial frequencies. That's one of the big advantages of the K2 camera. And it's these low spatial frequencies that gives you this contrast. It lets you tell if your particle is there or not, and especially if the particle is smaller, it makes it possible for you to see the particles in the image, okay? Now, if we have relatively high contrast from the camera, and we go closer to focus, I want to walk you through this for a second. So on the left is a relatively close to focus image, and on the right is a relatively far from focus image. And for many of you who've done this, you can see that, well, these particles look quite a bit nicer. And often in publications, this is what we show because, well, you can see the particles there and it's clear. But the high-resolution data is actually hiding in these particles, right? And the challenge here, and this is just a simulation of what the CTF curves would be from from two data sets. But on many microscopes, if you go far from focus, there's an envelope function which kicks in and limits your high resolution, whereas if you're closer to focus, that limitation is reduced. So you can make your microscope work better if you're able to get to closer to focus. Okay. So why am I talking about this? Well, one of the things I wanted to say was, with this energy filter, it's long been recognized that for thick samples, the energy filter helps give you improved contrast. And that's, so this is an example from Jan Loewy's lab, just a bacterial cell. But with a filtered image of a thick sample, you can see much better contrast. It's much clearer where the edges are. So this is one of the mechanisms where we certainly can't break sort of the thickness limits that Lou was talking about earlier, but we can, with the energy filter, will help you get the most out of your sample when you are trying to look through thicker samples. But the question is there any benefit to having an energy filter on thin samples? And to be honest, 5 years ago, people would have argued that the energy filter actually makes it worse. You know, there are problems with it. They would have suggested that because we're putting the beam through these extra set of optics, it's actually hard on the image, and it's better to not use the energy filter. And I think the results that we're seeing now suggest there's definitely no problem using the energy filter. And the question is there an advantage? And to be honest, this is a bit of an open question, so I'm speculating a little bit here, but I'll just walk you through some of the data that we're looking at. So there are data sets where people have collected images, both filtered and unfiltered, for relatively thin samples, and this is TMV that's relatively close to focus. The point here is that both this image, and if I just click here, I'm going to highlight some of the same areas. Maybe that doesn't make it easier. The thing to look at here is if you look at the edge of the carbon here, you can see that the samples are at the same focus value, so we're not playing tricks with defocus to try and see these particles better. It's actually by removing the inelastically scattered electrons, we're able to see these a little bit better. And this effect is always stronger the thicker the sample, and it's reduced as you get a thinner and thinner sample, right? And to just plot this, to try and be a little bit quantitative about this, what they did was they tried to measure the contrast of the TMV particles they collected as a function of defocus. And what you see is that the blue is the contrast they got from unfiltered TMV, and the red is the contrast they measured from filtered TMV. So you can see for thin samples, it's not a game-changing difference, but there's probably a 2 to 4% improvement in contrast for something as thick as TMV. Right. Okay. And so with that, right. Okay. And so I just wanted to show this one more time. So we think that the energy filter, it certainly doesn't hurt the resolution, and there's a chance that, you know, when the Sriram group is trying to get these structures that are sort of pushing the envelope, they're sort of scraping for every % improvement that they can get. And so they're using lower dose rates, and they're using close to focus images. And so we think that it's probably a small but not insignificant improvement in the contrast the particles could be coming from the filter. And the reason I say that is I know that many of you will be looking at systems, and when you're thinking about buying microscopes, there's often a thought that you should have a pre-filter camera and a post-filter camera. And the argument I would make based on this curve is that if you can get a filtered camera, the pre-filter camera really isn't necessary for this type of work, right? You can do all of the single particle work you want to do through the filter, and it certainly doesn't hurt, and it might even help a little bit. Okay. Right. And so the last thing I'm going to say about the direct detection cameras is that we are working on the next generation. And so we expect next year we are going to be introducing a successor to the K2 camera. And so what we're trying to do to help smooth that transition is that we're making the K2 cameras that people are buying now future-proof between now and the end of 2016. So we can't talk a lot about what this camera is, but we want people to be confident that if you're making the decision buying a K2 camera between now and the end of 2016, you're not going to fall behind with the technology that's coming in the future. Okay. So then the last thing that I'm going to say is I know there's been lots of talk about automation, and I want to just say a few words about what we're working on in terms of automation here today. Okay. So we've placed a lot of effort. We think it's a real priority to make sure that automation is a part of digital micrograph and part of the software that we're producing to run some of the cameras. And so basically the package Latitude S, we're in beta testing right now. We've got 3 labs that we're trying to put it through its paces and make sure it's delivering the performance that we expect it to deliver. But it's a full automation package like you would expect for collecting single particle data. Now, there are existing packages for doing this, and I just wanted to highlight some of the things that we focused on to try and that we thought were really important when we're doing this particular package. So, of course, everyone talks about ease of use, and that's something that we've strived to achieve here. I know with scientists, flexibility is also extremely important, and we've done a number of things to try and ensure that we don't fall into the traditional pitfalls of guided automation. Often you get a wizard and it has one way to do something, and you're doing an experiment and you don't want to do that. I have a reason I want to go a different way. And that's something that we've tried to make a part of the Latitude automation software so that you're not shoved into a single kind of experiment that you can do, but you retain the flexibility to do the things that you really have to do yourself. And so one of the ways we've done that is we've tried to make the wizards and the guides that go through the software less strict. And the other thing is that we've really tried to support scripting into this. And so you can imagine a number of steps the automated software is going to do. And each of those steps, we allow you to overwrite what we think you need to do in that step with a script, and so that you can do something else in that step as well. And so that's something that's there. We've really focused on improving stability of the system on a wide range of microscopes. So not only does this work on a Titan Cryos, which of course it will, but we also spent a lot of time making sure it works on TF20s and other more modest microscopes that maybe don't have the the special objective lens, the extra improved stability. So that's something that we're really focused on. And stability for longer continuous runs. And then something else that we've got a lot of feedback on that people really like is that we have these tracking and logging functions, which I'll explain in a second, which really give you a better idea of what's going on in the software. So let me skip to a few screenshots to just give you an idea of what's going on here. So this is our GMS3 software. It may look new to many of you. This is the successor to our GMS2 software. What you can see is we've really focused on trying to make it software controlling the whole system. So we have this image of the microscope on the left. You can click on things here. You can insert your OneView camera by clicking here. You can see in this case the beam is going through the microscope through an energy filter onto a K2 camera. And so the beam turns on and off, so you can get an indication of the status of the microscope. You can see on the lower left here, we have an indication of what's calibrated. Calibrations can change or go stale. And at every different magnification, you may need a calibration for something. And this will reflect in real time sort of what the status of your microscope is. So on the right-hand side, we have, rather than stick with a strict wizard, and this is what I was alluding to before, we have software which guides you the steps that you will need to take in order to do your experiment. And I'll tell you what almost everybody does, or everybody does a little bit differently, but people will start here, and then they want to jump down here, and then they want to go back here, and then they go back up here, and then they go down here again, right? And so rather than forcing you to do things in our order, we make it possible for you to have that flexibility to do the experiment the way you want to do it. Okay? And that's what we mean by a guided but not rigid workflow for the software. The other thing that we're focusing on is, because we're an imaging company, we're focusing on letting you use images to tell you how you want to align the microscope. And so what you're seeing here is someone has set up 5 different states at different magnifications. And so you can see this is a low mag state, intermediate, higher mag, and then this is the focus state down here. And you can see that in this particular example, we've been able to find a feature which we could recognize in these different images. And so we can click on the image to indicate where the same feature is at all the different magnifications, so that we can make sure that this mag and this mag are co-aligned perfectly. Okay? And that's something, rather than having to adjust knobs and iteratively work through that, this is something that you can do by clicking on images to tell you what you're doing. And we found that that's really, feels like the right way to do it. We've added things into the software that allow us to control the beam. So in this case, you can see that there's an image here that has the beam was shifted off of center. And so what we do is we will move the beam in different directions and take pictures, and then we will measure where the beam went, and this lets us try to center the beam. So this is what that shifting of the beam looked like before we did the beam correction, and this is what it looked like after. Okay, and so you can see this lets us correct the beam, even though the beam is something that's a little bit hard to see for cameras. That's the kind of thing we're doing. Okay, so getting into the nuts and bolts of it a little bit here. Latitude software is really about automating the single particle workflow. And you can see that we have a set of icons here which represent the different magnifications which you have for collecting data. So we have the lowest magnification image here, we have intermediate, we have our whole, or grid magnification, we have our whole magnification, and we have data collection here. And you can see this blue bar lets you highlights which images are actually being shown above for you to look at. Then one of the things you do is you mark the areas where you want to take a picture at a higher magnification, and it shows you the orientation and size of the image that you would be collecting at that magnification. It also marks what the other images would be at the next level of magnification. So you can see in this case there's a box here. There are a bunch of ROIs inside that which correspond to these ROIs here. And then again, this highlighted ROI here is actually the data that was collected here. And so this is actually data that we were collecting as part of a ribosome data set that was being collected. Right, and so then on this slide, what you see on the right-hand side, the way this works is it works asynchronously. You don't tell it to do one thing and it does that, and then you tell it to do the next thing and it does that. We really were inspired by Legion in many ways in this aspect. What happens is the software goes and tells a microscope to do something. And while it's doing something, you're analyzing, interpreting, and making decisions about what you want to do next. So it's not that you mark it and then it goes and does it, and you mark the next one, it goes and does it. It starts collecting some data, and then you start to identify the next things you want to look at. And as a result of that, it's off doing some things, and this is the way that it can tell you what it's doing now. So you can see these are all the images that it collected. You can double-click on any of these images, and it will show you the image you collected, the lower mag image, the higher mag images related to that image. So it's a way to navigate the images that you did collect, and to sort of manage that complexity of the experiment that's going on in the background while you're starting to interpret your data. Just one more screenshot of this. This is a lower mag view of what's going on with the software. And so you can see we have these atlas images. So this is the very low mag image. And you can see all the markings. So the yellow ROIs in this image indicate what has not yet been collected. Green indicates what has been collected, and blue is green is what's scheduled to be collected. So that's what the microscope's working on right now. And blue is what's already been completed. So I've already collected that data. You're free to go look at it, and you can try and interpret, understand what's going on with your sample. We're doing a number of other things. We're trying to reflect when you have the calibration for the size of the beam, it will reflect the size of the beam on your sample, on the image, so you can know if you're burning the adjacent region or not, things like that. So feedback like that to try and let you know what's going on. And then finally, giving you update for how many holes you've marked that are still unscheduled, how many holes you marked that are scheduled and the machine's working on right now, and then how many have been acquired. And this gives you a feeling for the total time that it would take to do what's currently scheduled and what would be, what's still, if you wanted to schedule everything. Right, I think that's, yeah, lots of detail. It's the kind of thing, we're actually pretty excited about this. This is kind of a really different way of using the microscope. We're pretty happy with how it's coming. So I think with that, I was just going to thank everybody for listening. Just a little screenshot for the cameras that we're working on. And if anybody has questions about any of the particular cameras, I'm more than happy to go into details about that. All right, thank you.
Thank you very much, Chris, for a nice talk. There's a small memento for you.
Oh, gosh. Wasn't necessary. Thank you very much. That's very kind. Yeah.
Thank you very much.
All right.
Thanks.
Thank you very much.
Questions? Any?
Of course, yeah.
The directions, it corrects while aligning, say, 400 frames.
Uh-huh.
So that is there in the software. It automatically aligns. I mean, I know that Ceres's group does that kind of, because direction could be anyway. I mean, it's not one
Absolutely.
way.
Yeah, that's right. No, so that's an excellent question. I appreciate you bringing that up. So what we will do is, we of course have a way to do whole frame alignment in images, but to be perfectly honest, I think the people doing leading edge work are doing other kinds of alignments. So as you point out, the Scherer's group doing particle polishing, right? So what we will do is we will give you stacks of frames that are unaligned, and you can choose to use, UCSF software for aligning it, or something in FreeAlign, or something from the Scherer's group. I think this is still something which is becoming more mature, but I think there's still people tweaking algorithms for how to best align particles, and you're certainly able to do whatever alignment you want to do, for sure.
Is there anything available in the Gatan software?
There is a way to do full frame alignment in the Gatan software, but again, I think that's okay for some particles, but I think if you're seeing sort of bowing or rocking motions, that's probably not what you want to do. You probably want to do something a little bit more advanced, and that's often one of the steps for the single particle reconstruction that comes later. Yeah. Go ahead. Yeah.
Thank you for the nice introduction. Actually, my first I have basically two questions. The first question is about is this package you introduced for the new working flow? It's very interesting.
Yes.
Actually, is it going to be, we need to buy separately, right?
Yes, yeah. It is a little bit separate. And to be honest, it's still beta. So we're still working on it. So it's not even released today either. Yeah.
So we're looking forward for that after.
Yeah, I think so. I would expect we're talking 3 months, that sort of time frame where we're.
Okay.
We're
in 2016 still.
Oh yeah. Okay, I wouldn't be allowed to talk about it. It was later than that. Yeah.
And the second question is about, since we are really finally, I'm very happy to see that our Gatan camera can start think about the diffraction, since very high dynamic range. But actually, even we use for the camera previously used for GIF. Sometimes for the zero lot peak, if we exposure time was played a little bit not properly, then we have oversaturation.
Sure.
So that's still sometimes we got very some bad background for more than half an hour or something.
I see. Yeah.
So how do you comment that if you with CMOS camera, you see exactly you get better performance? How do you comment on those signs if you still get a good barrel?
Yeah, no, and to be fair, I think for really intense beams, you would still have the same thing. So we do have this 833 camera, which we designed for diffraction to be more resistant to the high intense beams coming on the detector. Maybe we can talk about it a little bit after, but the one-view camera will still have the same effect, I think, that you're talking about there. Yeah. So if you're going to collect diffraction patterns, you probably still want to use a beam stop for the central peak. I think that's definitely.
Actually, based on that, if a one-view camera, do you think if we play with diffraction, we reduce our living time for the lifetime for the camera? Since
with the one-view camera, I mean, if you're playing with diffraction and you're burning holes in the scintillator, the scintillator will need to be repaired for sure, right? But the reason you would do that with a one-view rather than a K2 is that the radiation hardness of the K2 sensor is actually quite a bit higher than we were expecting it to be, but it's still not the same as a scintillator-based camera. And if I was doing diffraction, especially with students who were new, I probably wouldn't try and do that on the K2. I would focus on scintillator-based cameras or even something like this 833, which is a different diffraction focused camera. Yeah, right.
Another. Sorry. Maybe
please.
Well,
I just have a thinking. Just after your talk, I was thinking. So since it's now already CMOS design, it's different story. Reading out a strategy.
Yep.
So do you think it's possible? Actually, I have asked Ming before.
Yep.
Dr. Pan before. And do you think it's possible later on? Have a chance to expose different area with different exposures?
Different areas of the camera with different exposures.
Yeah, for the center beam, maybe you have lower exposure, higher angle, not higher angle. I mean, to the boundary, you have diffract spot maybe much weaker. You can use the longer exposure.
So
the hardware design, I don't know.
That would be something to think about. I mean, I think a stem. Well, even still, the undiffracted beam is going to land in the middle. I don't know how you would.
Yes, since now, to be honest, the beam stop on the camera on the microscope are generally ugly. They are either too fat in top, FEI, or too truncated for a gel, right?
Mm-hmm.
It's especially when you have. For example, you have a camera on very bottom, like from GIF.
Yeah, it's magnified.
You block the whole beam, and it's blocked the entire hole of entrance.
Yeah.
So then, if you have a beam blank, beam stop on the camera yourself, then you will get rid of this.
Yeah. And that's something we've heard that request a few times, and we're certainly trying to figure out what the best.
You have a beam stop inside a
GIF. Inside the GIF. I mean, that would be the right place to put it. You should put it down after that magnification.
Otherwise,
yeah, I mean, it's a good comment because that's something that we do hear from time to time for sure. I don't have an answer. I don't have a solution right away, but right, yeah.
Thank you for the.
Of course, yeah.
Yeah, thank you.
I have two questions. First question may be common to Lou and you, both the speakers in the morning. So, have anybody thought of a stereo electron microscope at all?
So rocking the beam, kind of, or
stereo electron microscope, so that you get the just like stereo zoom microscopes, you have three-dimensional perspective. Has anybody thought of stereo electron microscopes?
So you mean? So let me summarize to make sure I understand. So maybe so you would have sort of a left eye view and a right eye view.
So you get the initial model from the microscope itself.
Right. I guess that would involve rocking the beam back and forth. I admit I probably haven't thought too deeply about this. I don't know, Lou, have you thought about that at all?
Hello? Yeah, I think it depends on how complex the structure you're studying is. If you have like a very crowded organelle, for example, that's what I'm most familiar with, 2 views won't be enough for you to make sense of it.
Yes.
But if you have like 2 particles and you just want to ask how far apart they are because you know that they're not exactly in the same z-plane, then stereo, you can just use your stage.
Let's consider the simple example, single particle ribosome. So,
so I'm not sure. It depends on what you want to learn from the pair.
The microscope can give the initial model directly. So it's like
I mean, I think
it's like conical tilt. You have 2 projections.
So
you basically collect both the angles at the same time, and then you have the 3D reconstruction of that particle.
Yeah, that's so. I think
it's just like a microscope. Stereo zoom microscopes are used to pick crystals, so you have a 3-dimensional perspective. Yep. So similar to that.
So
Has anybody thought of? I'm
right. So I actually there's someone in R&D who loves that kind of stuff, and he's always recommending we do it. But I don't know. So in that case, So these samples that we're talking about here tend to be rather static. So having a live view stereo, which is what I was thinking you were talking about initially, you could imagine it being useful with in situ types of experiments, maybe a fluid cell, something like that. With this type of a sample, I think what Lou suggested, where you have a tilt, maybe 6-degree tilt. I think that's right. You tilt pair, yeah. Right. Right.
One is 6 degrees.
Yes.
rotated.
Right.
6 degrees, yes. That is the stereo.
Right, and then you put them side by side, and you put the glasses on, yeah,
Yes,
or you
that-
cross-eye.
That's
yeah.
a stereo view, yeah. Cross-eyed view. That's
I don't think we have automation to collect that type of data, but I've seen it done. Yeah. Right.
Maybe I'll just add that if you want like a plus 30 and 0 for a random conical tilt,
yes.
I don't think you can do that by beam tilt. 30-degree
Yes.
beam tilt above the
Beam
sample.
tilts is not possible.
Yeah.
Yeah, so you're
Yeah.
way better off just getting
Should,
most stages. I think
In
modern-
principle, it should be 2 optical paths actually. So for the source, there should be 2 optical paths for the source itself. If you want to achieve that in the same microscope without tilting.
Yeah, I think you
Yes,
need to
yes.
talk to FEI about that, right?
That's maybe the right way to
Yes.
do it.
And second, plus
Beam tilt.
minus 6 degrees, yes. Yeah. 6, 5, 6, yeah.
Yeah.
That gives a 3-dimensional view. Good. And second question was K3 Summit. What is it too early to ask? What is there in that?
Oh, what's the details of that? Yeah, that's the big question. So what we're saying about that camera at this point, so we still have lots of work to do. So we're being a little bit careful with the specifications at this point. What we're going to be able to say is that we expect a 4x increase in data throughput for this camera over the K2. So you can let your mind imagine what the specifications that would give rise to that, but we're going to exceed 4x data throughput on this camera. That's kind of the thing I could say.
I think the most important question is that if you are thinking of buying a camera now, from now till December 31st, the K2 Summit, you will be getting the K3 automatically as a upgrade.
All right. Yeah, this program came, to be honest, we really want to do the right thing. As we get close to a new generation, you hate to be the last one to have bought the last generation. So we're really trying to provide a way to sort of bridge that. So this is our way to do that, and it's not perfect because we can't, all the problems, we can't tell you everything about it, but you should have confidence in the K2 camera. It's gonna be really great, and the successor is gonna be great too.
Excellent. Thank you very much, Chris,
Of
for
course.
a wonderful talk
Yeah.
and discussion.